Hello folks, Dr. Young here. This is the last of those four ionic reactions, right? The SN2, SN1, E2, E1, and this will be the shortest video of all of them because like I'm going to say in a minute here again, they don't tend to happen all that much. E1's not going to be your major product for anything. It's just going to be a side product when you do SN1s. And let me show you what that's all about. So E1, E elimination again. 1 again is for sort of kinetics, it's unimolecular. So much like with the SN1, we know that the rate is just going to depend on, we have some sort of rate constant and only one thing, and it's just going to be the substrate. We don't even need a base for E1 reactions. They just happen. So like you'll notice, right, I didn't even write anything here. I didn't write any reactant, so no base. I mean, there could be a base around, but my point is that you don't need a base for an E1 for an E1 reaction to occur. Now let me show you the mechanism here. It's kind of weird and a little bit frustrating, but we do see that it occurs, and so this is how it looks like it occurs. I would do the same thing that I normally do, right, for any reaction. I'm going to go ahead and put my partial charges on here. And again, note that I don't have any like reagent over here. All right, I don't have like good nucleophiles, poor nucleophiles, weak base, strong base, nothing over here. So there's really nothing that can happen with my molecule except that I just wait for the leaving group to leave, right? So in that way, it's just like an SN1 reaction. I have to just wait for this leaving group to leave, and that's going to be it. And if I want that leaving group to leave, right, the point is that I need to have a really nice stable intermediate, right? So you'll note that this is a tertiary alkyl halide in my example, right? You're going to need to have that stable intermediate because you need to be able to get to that intermediate. So secondaries work great. Tertiaries work great. Secondaries work so-so. They're going to be a lot slower, or unless they're resonance stabilized, then they can be faster. But mostly we're going to see a lot of tertiaries for this. Now, in an SN1 reaction, we would have a nucleophile come and add to that carbocation, right? Top face, bottom face, etc. But again, I didn't add any reagent here, so there's no nucleophile to add. And so what's going to happen instead, just so that we can go down in energy, is that I'm going to lose a hydrogen from one of those beta spots, right? It's still an elimination, and it's still the beta hydrogens that are going to be the ones that go. And so now I have to decide, right, which of these beta, I have 3 sets of beta hydrogens in this case, which set am I going to pluck off? Or which, not even pluck off, which set is just going to fall off to make my alkene. And we decide by just following the Zaitsev rule, right? So you're just going to make the Zaitsev product. So I'll say follow the Zaitsev rule, right? So we're just going to look for the most stable alkene, right? Which is the most substituted alkene. So in my case, that means I'm going to lose one of these 2 hydrogens. So all that happens in this step is that the electrons from that hydrogen, they drop down to become part of the alkene. So I'm going to get my alkene in that spot. And now I have an H+, that H+ that just fell off, and I still have the Br-, right, which is why I wrote that stuff up there. So the E1 reaction is, it's just 2 steps. The leaving group leaves, and then a beta hydrogen falls off, and that's it. You're not going to see any minor Hofmann product. Most of all of it's going to be the Zaitsev product. It's going to follow the Zaitsev rule. You just make the most stable alkene possible. Now the energy diagram for that, right, if that's the mechanism, right, if the mechanism is simply just that the leaving group leaves, which gives us our carbocation, and then a hydrogen falls off to give us our product, then I really just have one intermediate, right? So I'm going to start with, I've got my starting material, I have a high energy intermediate, right? This is the carbocation. Here's the carbocation, and then in theory, I'm going to go to my lower energy alkene. So you just have one intermediate, and then you go to your product. So they're just 2 steps. So you'll have 2 humps, right? You'll have 2 transition states, one where the bromine's leaving, one where the H is leaving, and that's really it for your energy diagram. Nothing too fancy, nothing too crazy. And again, you can imagine I have this here. You can imagine that if you had something like a secondary alkyl or a secondary carbocation, that would be much higher in energy. So these reactions slow way down if you have to get up to the energy of a secondary, and even slower, right? You're not going to see it with the primary, but you can imagine it'd be even slower if you had to get up to a primary, and methyl would just be off the screen. So we're really just seeing these reactions occur with stable carbocation intermediates, low energy carbocation intermediates. So tertiaries or secondaries with heat, or maybe secondaries that are resonance stabilized. Now, what are the limitations? Basically the same thing, right? You just need, we need a stable carbocation. Stable carbocation. And since it's an elimination, we also need at least one beta hydrogen, right? You can't do an elimination unless you lose that hydrogen. So if I look down here at this first thing, yes, it is tertiary. That's great. That'll work. Here, that's primary. That won't. It's too unstable. The methyl will not work. It's too unstable. So these are no, no, yes. And now I go over here to this one, which is secondary, which is not as great, but it's secondary. It's a secondary cation. And actually, let me draw it out here. It's a secondary carbocation, but it's resonance stabilized. So it's actually going to be quite fast, right? You can draw resonance structures where that positive charge is delocalized throughout that ring. So when you have a benzylic carbocation, those are going to be real nice substrates for either SN1 or E1 reactions. And there's more more resonance contributors I could have drawn, but I'm just drawing these two. But this could do an E1 in theory, as could this one, because it's a tertiary carbon. It's almost exactly like the first one. And then lastly, this cannot, because again, all of these reactions, they cannot occur on carbons that are not sp3. So you're not going to see an E1 reaction occur on some carbon that's sp2 like I have in this example. So we're looking for tertiary, we're looking for stable cation. Now, as far as stereoselectivity goes, again, it's not really going to be an issue for E1. Not only because E1s are not major products, but because they always are going to form the most stable alkene. That's what you're going to see. So if I'm looking at this mechanism here, I'm just going to say, okay, well, the chlorine pops off. I'm going to get that carbocation, tertiary carbocation, and then I just look at my beta spots, and again, I look for I just follow the Zaitsev rule. So in this case, I've got 1H here. That's going to be the H I lose because that's going to give me the most substituted alkene. Now, in this case, there's not any stereochemistry like R and S or anything like that, but you would just always choose the most stable product possible. So choose the trans alkene, choose the E alkene, whichever one gets the biggest groups furthest away, that's going to be your winner. So you just try to form the most stable one. You don't have to worry about like anti-coplanar or anything like that like you did for E2. None of that applies for E1. They're very simple reactions, very straightforward, but again, they're going to be minor products. You don't really see them much. So the summary sheet, right, it's an elimination, it's first order. It only depends on the substrate because there is no base really that you need to use, which is why I said that it's irrelevant. The nucleophile bases, that doesn't matter. Substrates, just got to have a good carbocation, got to have a stable carbocation intermediate. And then the stereochemistry, you also don't have any special considerations. You just want to form the most stable looking alkene you can. That's going to be your major product for E1s. And then the solvents, it will happen faster in polar protic solvents, right? So protic is going to be where it's at for this one, because again, it's going to help that leaving group leave, and it's going to help stabilize that leaving group, just like it does with SN1. Now we have our chart here from before, right? We've filled it out with examples of poor nucleophiles, strong unhindered bases, etc., and all the reactions that we've done so far. And so I'm going to add E1 to our list of possibilities here. I can't do E1 with methyl halides, right? Because they are, that would leave a methyl carbocation, way too unstable. Never, ever, 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 ever suggest a primary carbocation for anything. A methyl or a primary, right? Don't suggest a primary carbocation for anything unless it's like super resonance stabilized. Secondaries are okay. They might require a little heat. You might have to heat those up, reflux them or something like that. But we're going to put E1 as the slowest, the last option for the secondary and the tertiaries. So we'll put E1 for those. Again, we'll see in a second, they're really just side products of SN1 reactions. And then for the nucleophile and base side, I'm not going to put E1 anywhere, because there's no reagent that I can add to like make a reaction go E1. If I add any of these things, something else is going to happen. It's either going to be an E2 or at the very least an SN1. If I add anything nucleophilic, probably I'm going to get SN1 reaction. When I form that carbocation, the nucleophile will add. So I'm not going to put E1 for any of these. So this sheet here is done. This is complete. This is all of the different ways that we can combine things and the reactions that they're most likely to do to give you your major products. Let's look at a couple of E1 possibilities. I'll show you with the last example where you might see some E1. But let's just say hypothetically for these first three, let's just say these are all going to go E1. Again, notice I didn't put any reagents for them. Just say they're going to go E1. So all I need to do is I just need to look at what beta hydrogen am I going to take off, right? So I've got a beta here and here and here for this one, which means that I'm going to take off a hydrogen from this spot. And that product is going to look like this. That would be the major alkene I would get if that substrate underwent an E1. Same thing for the one below it. I've got a beta carbon here and a beta carbon here. Again, it looks like that's the more substituted side and it has an H on it. So my major product, whoops, for this one would be where I formed the alkene on that side. It's the same story for all of these. Beta, beta, beta. Now these two are identical. They both have hydrogens, so you just pick whichever one you want. It's going to give the same product anyways. You could draw the alkene on the other side. That's just the same molecule flipped over, so that'd be fine. Now, here is an example. I'm trying to give you like a more realistic one, right, where we actually have water around. You know, that's a poor nucleophile. It's water. And so you may be thinking, oh, okay, look, I've got a tertiary alkyl halide. So it can do E2s, it can do SN1s, or it could do E1s, right? Those are the options. And now I have a poor nucleophile. Pretty much they can only do SN1s, so therefore I must be doing an SN1, is the idea, right? Because your chlorine's going to leave. You're going to get a carbocation. And now your water can add to this to give you your product. Right after two steps, water adds, then the H leaves. I'm skipping that step just to show the product here. So you'd expect this to be your major product. But the idea is that you could also get a little bit of the E1 here, right, to give you a minor product. So realistically, if you did this reaction, you'd probably get just a little bit of E1 side product, right? Just because you have a carbocation here. You have a carbocation, you have hydrogens on either side of this, right? Beta carbons, beta hydrogens that could, you could lose the hydrogen and make the alkene. So you're going to get a little bit of minor E1 product. For this chapter, that's pretty much all we're going to see E1 as, is basically a side product of when you do SN1s. Now we'll see in the next chapter when we talk about alcohols, we're going to see a lot more E1 for alcohols and the dehydrations of alcohols. But for right now, E1 is just kind of like a cruddy little side reaction. It's not going to be a major product for anything. There's no reagent I can add to force something to go E1. And that's all I have to say about E1s. That's it. So study up. You should do lots of practice trying to figure out, given a set of reagents, are we going to go SN2, SN1, E2, or E1? So study up, do some practice, and watch the next video I'm going to post, which is more on solvents and better explaining how the solvents affect the reaction rates for SN2 and E2 versus SN1 and E1. All right, good luck.